Today we are going to start motional electromotive force, motional EMF. For this, first of all, we should know what is the motional electromotive force. The induced EMF produced due to the motion of a conductor through a uniform magnetic field is called motional electromotive force. To find the expression for the electromotive force, we will consider here a rectangular loop and we will name this P, Q, R, S, and now it is placed in the uniform magnetic field which is perpendicular into the board. This is the sign of magnetic field into the board. So this whole rectangular loop PQRS is lying in the magnetic field, and remember now magnetic field is into the board and PQRS is the rectangular loop. Suppose B is the strength of the magnetic field. This RS arm that can move on this PS and QR without any friction. And suppose this length PQ and RS will be equal, and that will be equals to suppose L. Now this arm SR is moved by a constant velocity V towards this PQ in this direction. This is the value of V. Now we are going to find out first magnetic flux linked with this loop. So phi B, this is the magnetic field. This will be equals to the strength of the magnetic field B into its area, and now area equals to of this one. If suppose distance of QR, this equals to X, and this width L, then L into X will be the area. So A equals to L into X. So we can write B L X. This is here the magnetic field. What we know here, according to Faraday's law of electromagnetic induction, so induced EMF in this circuit, this is here in this circuit, is epsilon naught minus d phi by dt. So put the value of phi b from here in this equation. This is minus d phi b. In the place of phi b we will write blx, d by dt blx. We know very well here B and L, this L and the strength of the magnetic field both are constant, so we will keep it out, minus BL d by dt x. We know also d by dx by dt, this equals to b, and think over this here now. When it is moved in this direction, the value of x decreases, so we can say minus dx by dt equals to b. So in this equation we can write b flux linked with this loop, this equals to minus bl, and this is equals to v. So this is here the formula for the motional EMF when a loop is kept in a uniform magnetic field. Now conclusion, we can see here this minus will be cancelled, BLB only, this minus here B, then here we can say this magnetic flux or UMF, sorry here, this will be here epsilon, induced EMF. This induced EMF is equals to BLB. So its conclusion is, we will see the EMF depends upon B, L and V. So we can say EMF induced in the conductor is directly proportional to B, directly proportional to L and directly proportional to velocity of the conductor. Now suppose this loop has its resistance R, then current flowing through this conductor I, that will be equals to epsilon by R according to Ohm's law. Then this equals to BLV by R. So this is here your result. Thank you. In the next video. Now today's topic is motional induced EMF in a conducting rod rotated in a uniform magnetic field. So let us consider here a rod, conducting rod. This is PQ. This is the conducting rod. Its length is L and O is this P is fixed at this point P, and it is free to rotate about this point P. This can move in on this one like this or like that. It is free to rotate about P, and it is kept here in a uniform magnetic field which strength is B. Strength is B. It is kept here. Now it is rotated in this direction with angular velocity omega. It is rotated in this direction with angular velocity omega, and magnetic field as shown as here now by the cross, that means the magnetic field is perpendicular into the board. So this rod PQ is moved, and this point, this end comes to this point Q dash after some time T, and this OQ describes here an angle alpha. So value of this arc will be L into alpha according to formula theta equals to L by R. So this OQ dash is equals to L into alpha. So we will use when we are going to calculate the induced EMF of this rotating conducting rod. So now magnitude of the induced EMF across this rod PQ. According to Faraday's law, this equals to d phi b by dt, and we know here phi b equals to BA. Now we can bring it B outside, then B d by dt A. Now we are going to find out value of A of this one. So area of the closed loop, this will be equals to half into this arc Lx, L alpha, into this L. This will be equals to half L square alpha. Now we will put this value here in this equation. So induced EMF is equals to this. So this equals to B d by dt, and here in the place of A we will write this half L square alpha. We know here that half and alpha square is also constant. So we will bring it outside, half B alpha, then d by dt of alpha. So d alpha by dt, this equals to omega, angular velocity. So here we can say it is L square. So this equals to 1 by 2 B L square omega. So this is here the final value of EMF. So I think this is very important, and you will find in the NCERT book for a cycle wheel attached with some spokes. So we will see that portion. We can easily solve this, but here now there is some problem. I think I am going to discuss here. Suppose this is a wheel of a bicycle, and here are some spokes. Spokes are connected to the rim, and we will see rim is also metallic. So in the question it is asked EMF, what will be the EMF between axle O and this rim. So here you will find this is this, all the spokes are in parallel like this. So EMF induced in this one, that will be, suppose this induced will be here, that EMF between this spoke will be the same. So you will find that between this and this, EMF induced in a rotating cycle spokes or cycle wheel in a uniform magnetic field have the same EMF. Thank you. Now in this class we will learn about the dissipated power in a conductor moving in a magnetic field. So let us consider a rectangular conductor ABCD. we will consider here A, B, C, D. And we should know here that AB is movable, that can slide without friction, and length of AB is suppose L. So arm, this AB is now moved or it moves in this direction with velocity V. So motional EMF induced in this arm AB is equals to BLV, epsilon naught equals to BLV. Now induced current, value of the induced current in this arm AB is equals to this by R, where this R is the resistance of this AB. So here we can write BLV by R. I think it is very clear. Now, according to Lenz law, direction of induced current in the rectangular conductor is clockwise in this direction. So current will be induced in this loop clockwise. Now the force acting on a current carrying conductor, this equals to force F on this current carrying conductor F. This equals to I L cross B, where this B is the magnetic field which is perpendicular into the board. Here. So this equals to, we can write I L B sine 90 degree. Why sine 90 degree? L and B, this is the L and B is here, so both are at 90 degree, so we will write 90 degree. So this value becomes 1. Now putting the value of I, this from here in this equation, so we will write B, value of I BLV by R into I. This can be written as B, then L square, I is not here, I is written, B value of I and it is L. So L square, B square, L square, V by R. This is the force. So according to Fleming's left hand rule, direction of force is in the direction opposite to the direction of the velocity of this conductor AB. I repeat it now. Direction of the force in this is in the direction opposite to the direction of the velocity of the conductor. That means it will act in this direction. Since conductor AB is moving with a constant velocity, so force equals to the magnitude of the force to be applied on the conductor AB, this to counterbalance the force on the current carrying conductor AB places in the uniform magnetic field. Now we know very well that rate at which work is done to move the conductor AB with uniform velocity V, thus power equals to F into V. So value of F is here. So we can write B square L square V by R. This is the value of F and V. So this equals to B square L square V square by R. This is the power, which this power to push the conductor with constant velocity perpendicular to the magnetic field. Now, the rate at which thermal energy appears in this arm. So according to heating law, Joule's heating effect, so we can say that power is equals to I square R. We know the value of I and R also. So this will be equals to what now? I equals to, this is value of I square, that will be BL V by R, this whole square. This is, and this into R. So this will be equals to B square L square B square by R square into R, and this equals to B square L square B square by R. So we have seen here now the power, this and this power, both are same. So this power is dissipated in the form of heat per second in the conductor. So we can say the mechanical energy used to move the conductor in a uniform magnetic field is changed into electrical energy, which dissipated as heat as per Joule's law of heating. Thank you.